Hello, welcome back. In this segment, I want to discuss an interesting problem that is mentioned on this book. The problem number 45 is an exercise problem. Let me read this problem for you. We would like to distribute some information to S people, okay? S is an integer, of course, positive integer, so that if any two of the S people combine their information, they can deduce the secret integer k, okay? So you have some secret, and you are going to split the secret key k among S people, okay, in such a way that one person alone cannot recover the secret key k, but if you get two of them together, you can rebuild the key k. That is basically this problem. Okay, so what they're saying here is that select a prime number p larger than S and k. Remember, S is the number of share or number of people you would like to distribute, and k is the secret key that you would like to split. Select a polynomial f of x, which is a times x plus k. Polynomial is defined in ZP. What it means is that all the operations are done in mod p, okay? So you will never get an answer more than p, of course. All the numbers are from 0 through p minus 1. That's the meaning of this ZP of x, okay? And a being not equal to 0. If a is 0, you will directly send a k, which is bad because you don't want to send a k to anybody. That is the reason why you will make a to be not equal to 0. Okay. Compute the pairs I comma f of I. Okay, I is an integer, positive integer running from 1 through s, inclusive of 1 and s, and distribute these pairs to s people. Okay, now we need to think about, well, we have to prove that this scheme has the desired properties, meaning any two people, any two of the s people can combine their information, and one person alone cannot do anything. That is the goal of this particular problem. Very nice problem. It has immediate application to cryptography, as you will see soon. I'm going to actually show to you that if my key k is a, say, 256-bit number, I can split it among s people, and if any two of them provide me the share, I can rebuild the original key k. That is the idea. You can use it for key management, for example, to store a key at different nodes, so that later you could combine the key and rebuild the key k. Okay, that's basically the idea of this particular problem. Okay. When I first saw this polynomial, it was an interesting connection to the affine ciphers that we discussed earlier. In one of the segments, I talked about affine ciphers. If you compare the affine ciphers with this problem, there is no difference actually. F of x is we treat x as a message. We treated a and k. In that segment, we were using b because that's how we were defining it. We said f of x equal to a times x plus b, but you can replace b by k. It's the same, just a notation. And we proved that affine cipher is just a permutation, meaning I'll show you to you very quickly now. So let me generate an affine cipher, affine mapping for p being 5. Okay. You can take any Latin square you wish. Okay, this is the same affine mapping I have discussed with you in the past, so I didn't change my program. You see here, the message space can be either 0, 1, 2, 3, 4, because we are limiting to the prime number p to be 5. And on the book that I just shown, it is a and k, but earlier we were using a and b, so I just wanted to show to you. The point here is that if you know only one value from this matrix, okay, we don't know a and b. Now let me change the syntax so that we get according to the book syntax a notation, right? Let's see. We define f of x is equal to a times x plus k, right, in mod p. Now the question is, suppose you found only one pair, okay, meaning for some reason the ith person leaked his I and f of I. So what happens in that case? The attacker has the pair I comma f of I. Can he do anything with it? I'm going to show to you he can't do much. Suppose I know my I was 4 and f of I was say 4. Can I say anything about a and b or a and k? It turned out you can't, because you see, let's say I know my x, my I is 4, right? That means this, my I is 4 here, and I know the corresponding value is 4, but it could be a being 1, b being 0, or k being 0. I'm going to use K now to be consistent with the formula. So A to be 1, K to be 0 is one possibility. Go to A being 2, A being 2, B being 1, or K being 1 will also give you 4. So if you see a 4, it doesn't really tell you anything about the corresponding A and K, okay? Because 4 occurs, you're going to only focus on this last column because somebody said, okay, I leaked the pair 4, 4. That means you know it's 4 here. And you look at last column, you know, in the last column, the 4 occurs here once, which corresponds to A being 1. Here it occurs with the A being 2. Here it occurs with the A being 3. So all possible A's are possible. Similarly, all possible B's are also possible, except the B corresponding to A being 0. That's why it's a perfect sequence scheme. If you assume that all the shares are properly distributed and stored, there's no way you can break, because you have to try all possible values. And even if you try all possible values, you cannot tell exactly which A and which B or which A and which K are used by the guy who's distributing the share. Okay. Anyway, so that's basically the motivation. And now it's clear what happens if I have another pair. If I have another pair, the problem becomes much easier to solve. Let's say I got the jth pair and corresponding f of j, right? How can we solve now and find A and K? Is easy. Since we are given I equal to I and f of I is nothing but A times I plus K in mod P. Okay. And f of j is equal to A times j plus K in mod P. You just subtract both of these equations, and then you will know immediately the value of A. Okay. So if you subtract, the reason why we work with mod P should be clear in a minute. Okay. If I subtract these two, what will happen is I get f of I minus f of j. And this is nothing but, if I divide it by I minus j, I get A. Okay. It looks like fraction, decimal, that kind of thing, but you should not worry because we are working with mod P. This really means I minus j inverse. So I can say I minus j inverse. Okay, so I can get rid of this. Okay, is equal to A. So you immediately found A. Once you know A, you can go and substitute because you know f of I, you know A, you know I, of course, because you selected I comma f of I. As an attacker, you found I comma f of I. Okay, somewhere somebody leaked that. Okay, then you know I, you know f of I. Because of the other pair, if you found another pair, of course, then you're breaking the system. The idea is that breaking only one should be not sufficient. You should be breaking at two places. Okay. So if you know A, you know I and f of I, you can find the K immediately. That's the idea of the system. Okay. So let's step back and look at the problem again. The problem is that we need to take the secret K and split it into S parts. Okay. How do we split that? We just call this function f S times, right, for all I from 1 through S. So that's what we are going to do now. Okay. P is a public number. Okay. How is P selected? P has to be greater than A, as mentioned on the book. That means all the elements are within the field P. That's basically the idea. And the number of shares that you're going to do, P is also greater than S. Okay. All right. And A has to be not equal to 0. So now you compute the f of I comma f of I, 1 less than or equal to I less than or equal to S. Okay. Master will send it to this node safely, and of course anyone monitoring this traffic should not be able to understand what f of I is. Otherwise they will know all the shares. Okay. Somehow imagine nodes are abstraction. So it could be file system or anything where you put all these things in different places securely. Okay. So that's something that I leave it to you. It could be a cloud service, or it could be a file system with different permission levels and so on. You are able to distribute the master key K across multiple nodes. This is the logic you're doing now. You are computing I comma f of I, and you're sending here to this node f of 1, and here you're sending f of s. So each node gets its share. All right. Now the key k. Okay. Already, I have to say one more thing. The p must be greater than k, otherwise k will wrap around in mod p. Okay. Now, how are you going to reconstruct this now? Suppose node 1 or node I and node j are available, and the rest of the node died for some reason. Okay, here is node I and here is node j. There are two nodes. Only two nodes need to be available online, and this node will send it back its f of I, and this node will send it back its f of j. Okay, so how are you going to now compute the? This is jth node. Okay, how are you going to compute the key k now? Remember, you're not storing key k anywhere. All you're now going to do is just make use of this nice thing, right? You're going to plug it into this formula, as I explained earlier, and you're going to compute f of I minus f of j divided by I minus j inverse, divided by I minus j, which is same as multiplying it by I minus j inverse in mod p. Okay, this is going to give you your A. Once you find the A, you can plug it in to this model to find the k, because you know I, you know f of I, because the node I, for example, send it. You can also use node j's value, j comma f of j, doesn't matter, and you can immediately find the k. So that's basically how you are going to reconstruct the original key k. All right, let's do a quick demo. I think this is fun. So remember, this is just an affine mapping. We talked about affine mapping and chosen ciphertext attack. I mentioned earlier that you would need two plain text ciphertext pairs to break a affine cipher. This is actually a very nice application of cryptanalysis to something more constructive side, how to store the master key. All right, let's do a quick demo of the sharing aspect. Let's first generate. Okay, let's generate an AES key, for example, random bits of say 256 bits. Okay, I wanted to put it at 5 places. Okay, and I'm going to now share this key among 5 different nodes. The key k is what I wanted to share. Okay, so now I get 5 elements in the array. I'll explain to you in a moment. I leave the first element because I always put the first element mapped to 0, just to make the I comma f of I mapping clear. Don't worry about the first element. Okay, so the first node gets this value. This is the I is equal to 1 node, 2, 3, 4, and 5. And what is this one? This is the p that we need, of course, the mod p. So this is p. So we got the p. Okay, and now we have to assume that the master already sent these values. This is for the first node, this is for the second node, and so on. Okay, and let's now try to reconstruct it. Let's say only the third node and the fourth node are alive, the rest of the nodes died. Okay, now can we reconstruct the same key k? So I equal to 3. Okay, what is f of I? We need to compute f of I, which is nothing but the third element in this array. This is 1, this is 2, and this is 3. Okay, this is the third element. Similarly, I need to take j to be, say, 4, or take 5, doesn't matter. And let's compute the fifth element value. Okay, this is the fifth element share. Okay, now we are ready to reconstruct the whole thing. We wanted to be able to reconstruct the key k. This should come out. Let's try our luck now. Reconstruct the key using I comma f of I, j comma f of j, and the publicly known mod p. Hopefully the key k will come out. All right, you got the key reconstructed. We can confirm that same as the key that we wanted. Key k, yeah, you see it's the same. exactly the same. The Python shows L for long type, but other than that, it's the same. Okay. So what it means is that you have, let's go back to the picture, right? What did we do? We have this k that we wanted to distribute among nodes in such a way that k is transformed into some other number, right? By applying this transformation using the function f. So node 1 will get some share of k, node 2 will get some share, and so on. If any two nodes are alive and they reply back with their corresponding shares, we can reconstruct the key k. Okay. Why do we need mod? If you don't have mod, I'll show to you what will happen in the next segment. But for now, assume mod is helpful for avoiding a decimal division by dividing by fractions and decimals and whatnot. You can get rid of that because you can do multiplicative inverse. The mod will also hide some patterns regarding how the values are distributed, the values of a and k. I will talk about that later, but this is good enough for now. Very quickly, I will now show you the Python implementation. So it's just a demo proof of concept implementation. We decide how many people in our system, how many nodes. Yes is the share, right? K is the key secret that you would like to share among the yes people. What did we do first? We need to generate a prime number p, which is greater than yes and greater than k. That's the reason why I do this. The plus one is just because this random prime number can be generated with the lower bound. Okay, this is the lower bound. Okay. All right. And then we generate a random a between one exclusive of p. Remember, a must be within the field zp. That's the reason why I'm generating a. And then I ask the gen shares method that will essentially apply this function f on different x values, meaning different I values running from 1 through s, and applies this function for different I values, and then returns the shares. Shares are just content of the transformed key k. Okay, nobody can reconstruct the key k just from the shares. They need enough number of shares. In our case, we need 2 shares to reconstruct the key k. All right, that's basically it. And then the random number generator is using this traditional random number generator and check whether it's prime. Once the prime is obtained, we return back. That's necessarily it. A reconstruction key is given here. You will feed I f of I, j f of j mod p, and then you will construct the inverse of I minus j. And as I explained on the whiteboard, you do f of I minus f of j and multiply it by inverse, and that will give you the a value. Once you know the a value, you can reconstruct the k value. Just go and plug it into the formula, and that's basically what I'm doing here. That's all. So that's the reason why we are able to successfully reconstruct the key by distributing the key k among s nodes, and only need 2 nodes to be available. Okay, any 2 nodes. I have randomly chosen 2 nodes, 3 and 5. You could choose 1 and 4. We can also confirm it very quickly. Let's do that. Let's select j to be 4 instead of 5. Okay, this is where is it? J to be 4 means this one, right? Yeah. So let's do that. Let's do j to be 4 and fj to be this, and see whether we can reconstruct the key and get the same key. Yeah, you see it's the same key as key k. That's pretty neat. And the whole thing is a very nice construction. Unbreakable from an information theoretic perspective. It doesn't matter how much effort the attacker puts. They can't find a and k from the share. If they only broke into one machine, one of the nodes, they cannot reconstruct a and k. They need to break into 2 places. Okay. I'm also assuming that the nodes behave properly. If the nodes send the wrong values of the share, the system will not work. There is something called verifiable node secret sharing, but I will talk about that later. At this point, it's good to know that this nice mathematical model is just an instantiation of a Affine cipher in a different context, allow you to distribute the master key k across multiple nodes. Okay, that's all. Thank you very much.